Hey everybody, and welcome to our next video in food chemistry, which we are going to focus on the three states of matter. So solids, liquids, and gases. But before we get to that, I want to talk about, or think about rather, what it is you do a lot in the kitchen. So if you look at this image, right, you see this woman and she is smelling whatever she has made. Okay, and you see that little cloud of smoke that's there. It's not actually smoke, but it's vapor. And what is it that's inside of that vapor that allows for us to smell all of these delicious or not delicious smells that you can produce in the kitchen by cooking via primarily the Maillard reaction, which we've already talked about. So what's happening in that little cloud? And so I tried to draw a little cloud right here. So we're going to pretend that whatever is in this image is in this image as well. And a lot of that is not actually smoke, but it's steam. And steam is going to come from water molecules. So all of those right there are going to be your water molecules, and most of that is going to be water. However, there must be something else in there in order for us to smell these smells that come from whatever it is that we're cooking. And there are thousands upon thousands upon thousands of different compounds that we smell that are vaporized when we start to cook something. So for example, I just listed 5 in here. Now these structures, we're not going to get into really what these structures mean per se. You might see some of them as we talk more about this as we do progress throughout this unit a little bit. But all of these different compounds, other than water vapor, contribute to a certain smell that you're familiar with. So for example, that one in the bottom corner right here, the bottom right-hand corner, that's maltol. I'm not sure how to pronounce that. But maltol is the scent of fresh bread. We have allicin up in the upper left-hand corner, and that is going to be garlic. In the middle, right here, we have 2-pentylfuran, and 2-pentylfuran is one of the components of the cooked smell of bacon. We also have vanillin, which is very common. I know you all know what vanillin smells like, but vanillin is typically found in vanilla, and you smell a lot of that in any type of baked good that you might find. And this last one I have up here has a crazy name. It's ZZ36-nonadienal. Now, there's reasons why it has that particular name. We're not going to go into that, but this is the primary scent that you find in fresh watermelon. So all of these right here, plus thousands of others, contribute to those smells that we attribute to certain things in the kitchen. And we're going to talk more about this because I have a lot of things that we can do with our sense of smell throughout this class. But as we know, right, all of these are gases. So when you smell something, the reason why you're able to smell it is because that particular substance is in the gaseous state of matter. It is a vapor. So if I look back here at this image before, if you smell something, especially if it is hot on the stove, there are lots of vapor molecules that are coming off of that. And when you smell those vapor molecules, they go into your nose. You accompany that with a particular scent, and those therefore are gases. So here's an example of what a gas would look like. So lots of properties about gases. Gases, we could talk about gases for weeks. In fact, I do that in my Chemistry 2 class. So gases are really special. There's a lot of things we can discuss about them. But anyway, gases tend to take the shape of the container that they're in. So when you are cooking something and you have a lid on top, those gases take the shape of whatever pan with the lid on top. You take that off and the gas comes out. And that's because they take the shape of that container. That's also known as diffusion. Gases can diffuse very easily. They'll travel throughout. And the reason why is because of something else we'll talk about here in a second. Gas particles are very far apart relative to their size. So we could see that here's a gas particle and here's a gas particle, but there's a lot of space in between those particles. Same thing here. Here's a particle, here's a particle. There's a lot of space in between them. So the particles themselves are very small relative to the space that's between them. And as a result, we can take gases and force them to contain a smaller space. So I could take this gas and make this container that it's in half the volume. What does that do? Forces the particles a little bit closer and therefore will increase the pressure. Particles of a gas are constantly moving. So because gas particles are constantly moving, you'll see here that there's arrows in this image. The reason why we have all of these arrows is to show that these gas particles are moving. This is why gas particles diffuse throughout the room. So if you're cooking something in chef's class in her kitchen and people walk by and they smell that, right? Why do they smell that even though they're in the hallway? That's because gas particles have enough energy that they can move from one place to another place. That's called diffusion. They're going from an area of higher concentration to an area of lower concentration. The pressure of a gas depends on how frequently the particles are colliding with the container walls. So here, for example, you'll see that some of these particles, if they're constantly moving, they're going to have to collide with the inside wall of the container. If you think about a can of soda, right? There's gas particles, there's gaseous CO2, carbon dioxide that's there. And that is under a lot of pressure. The reason why is because we forced a lot of carbon dioxide in that tiny bit of space that's on top of the can. And as a result, those gas particles are touching that inside can very, very frequently. That leads to an increase in pressure. So the more those molecules collide with the walls of the container, the higher the pressure. Let me move my little image here. Higher temperature gas molecules move more quickly. So what we're going to see is that if you have something that smells when you cook it very strongly as Brussels sprouts, okay? You cut a Brussels sprout, doesn't really smell that much, right? Whereas after you cook it, when you heat it up, those particles, you smell it very strongly. Why is that? Those molecules that you have raised the temperature of, and as they became a gas, they have more energy. And if those gases have more energy, they want to travel more. So as a result, they will move more quickly and disperse throughout the room. So higher temperature means that these gases will move more quickly. Last thing that I have, higher temperature gases will take up more space. And there are so many gas laws that we are not going to get into. I taught gas laws to my chemistry 2 class. I think there are 7 gas laws that they have to remember. One of those gas laws is Charles's law. And Charles's law says that the higher the temperature of a gas, the more volume that gas is going to take up. And that's because if those higher temperature gases are moving more, they want to take up more space. A lot of chemistry goes into gases. We are not going to talk about all these types of things that you need to know for liquids and solids. But anyway, I found this really cool video online because I wanted to show you really how strong gases could be. So I talked about a can of soda before, and I found this video of a soda can that exploded in a hot vehicle. So we're just going to watch a very short clip of this together, a video of watching a video. It's kind of interesting. But like we said, you have that soda can. And in that soda, you have whatever the liquid is, and they put carbon dioxide gas in there, and then they close it up, but it's under a very high amount of pressure. And when you leave a can of soda in a hot car, what's going to happen? Well, as you could see here, we're going to go ahead and look at the beginning of this a little bit, and then I'm going to skip ahead to the end.
Now this shows just how hot it is today. This can I found here must have been left in the vehicle yesterday, and in the heat it seems to have completely ripped the top off. You can see the contents inside, and you can see where it must have spilled or sprayed around the area here. The rest must have oozed over the side here.
So as we could see, that now this video, I don't think he said it yet, but he's in southern Texas, so it is very hot there. And we'll look at the end. Actually, let's go to the end now, because he takes an infrared thermometer and he starts measuring the temperature of everything. So let's skip ahead and watch that a little bit.
131 degrees. Upholstery of a car. 145 degrees. Dashboard of a car. Black car. 179 degrees. What do you think about that?
So that vehicle is very, very, very hot, okay? When you have that can of soda and that gas inside of that can of soda gets so hot, those gas particles are moving a lot more because the temperature is related to how much the gas is moving. That's what the thermometer does. It basically measures how fast particles are moving. So when this car got that hot, those gas particles in that soda can were hitting the walls of the container so often that can couldn't withstand that pressure anymore, and it exploded. Okay, so be careful when you put your hot soda cans in a car. Maybe it's not so bad here, but definitely you could see that this can happen in a place where it does get very warm, like in southern Texas. So let's go ahead and relate this more back to food, right? So these senses of smell that we have and these gas particles, there's a certain phrase that we can use to identify what types of molecules are these smells that we smell in the kitchen. And we call these volatile organic compounds. Now, a lot of times people think of the word volatile as meaning bad. Volatile does not mean bad. Volatile just means that it evaporates quickly. So volatile organic compounds, what they are, is they are low molecular weight compounds that have very low boiling points. So if something vaporizes at a very low temperature, that means that it is a gas, primarily at room temperature, or we can get it to become a gas at room temperature with just a little bit of heat. That's what volatile means. And the word organic just means that that particular compound is primarily composed of carbon, hydrogen, maybe some oxygen, nitrogen, sulfur, phosphorus, some of those types of elements. So anything that you smell is a volatile organic compound, especially in the kitchen. And there are, like I said, thousands of volatile organic compounds. I found these two great images online. You can find more of these on compoundchem.com. But you'll see that here's some aroma chemistry of fresh baked bread. There's not just one compound that contributes to the overall smell of bread. There are many different compounds together that give us the scent of fresh baked bread. The same thing goes with frying bacon. Okay, you could see here that 150. There's about 150 compounds that contribute to the overall smell of bacon. There's not just one. So we're talking thousands upon thousands upon thousands of different compounds that we smell probably daily when we're cooking in a kitchen. Let's take a look at the second state of matter, though. The second state of matter is a liquid, and these two are not going to take us as long. I really wanted to focus on gases. Liquids, on the other hand, tend to look more something like this if we look at a particle diagram. And liquids take the shape of the container that they're in, and that's because the liquid particles could slide past each other. So they don't have enough energy to totally break free from one another, but they do have enough energy to slide past each other. So what we can do, this image isn't showing it here, but this particle can technically move all the way over here. And this particle can technically move all the way over here. And this particle can technically move all the way over here. They could slide past one another because they have enough energy to do so. As a result, they take the shape of whatever container that they're in. I take some liquid, it's in a carton when I buy it. I put it in a mixing bowl, I put it in the pan, I let some of it evaporate, I put it in my dish. Okay, it always takes the shape of whatever container it's in. Liquids do have a definite volume, though. I cannot change the amount of volume of liquid. If I have, 32 ounces of water, I can't make that 32 ounces of water become 20 ounces of water because those particles are already very tightly packed. Lastly, let's move my picture again. Liquid particles are much closer together than gases, than gases. So they're touching each other, but they're not in a very organized pattern. So you'll see here that yes, a lot of these particles are touching one another, but they're not very orderly. And we're going to see the difference with solids here. So I just found this image. You have some chicken broth and some flour. A lot of times you can use this mixture in order to thicken up a sauce. But this particular substance is a liquid. This happens to be a mixture, not a pure substance compound. Most liquids you'll find in the kitchen are mixtures because the solvent is going to be water. And we'll talk more about solvent, what that means in a later unit. But this, you could see, takes the shape of whatever container it's in. And that's because those liquid particles have enough energy to slide past each other. Lastly, let's talk about solids very quickly. We can clearly see the difference here between the particulate diagram from liquids and solids. Solids, you could see, I can't make these particles any closer to one another than they already are. These are in a very orderly arrangement. Solids have a definite shape and they have a definite volume, and neither of which can be changed. So I can't take a solid material and make it take on another shape. And that's because they are stuck in place. They are very rigid. Solid particles, like we said, are in a very orderly arrangement. And this is because the particles actually don't move past one another. These liquid particles will only vibrate back and forth. So they just do this next to one another. Because they're not sliding past one another, they are going to retain their shape. Lastly, solids are the most common state of matter that's found on Earth. I saw something as I was making this PowerPoint. I think it's about 99.85% of everything on Earth is a solid. That makes sense. We're not going to get into the types of solids really, but yeah, I think makes a lot of sense based on the chemistry aspects behind it. So most of the things that you work with in the kitchen are in fact solids. Okay, you see some oil over there off to the side. That is a liquid, of course, has different properties than all of the solids that we see in this picture as well. Not as many gases, but I wanted to talk more about gases because first of all, they have unique properties. And second of all, we use our sense of smell quite frequently in the kitchen, and that comes as a result from gases. So just to reiterate one more time, here are the three states of matter. So we could see in this first beaker, all the way over to the left, I have a solid. That solid has retained its shape. It's not taking the shape of the beaker that it's in. And you'll also see those little lines on the outside of it. That just means that those particles are in fact vibrating in place. You could see the liquid is in the center. Those liquid particles do take the shape of the container that they're in, and you'll see that there's little arrows that are there. Those little arrows are showing that liquids can in fact slide past each other, and they slide past each other. As a result, they take the shape of their container. Gases, on the other hand, all the way over to the right, you'll see they are very far apart relative to the size of the particles themselves. You'll see they have very large arrows to show that they are moving much more quickly than the other ones. We also see that it does take the shape of the entire container. It fills the whole entire thing. And that's because gases like to be as far apart as possible. They will diffuse, they will move in order to take up that whole entire area that they're given. We're going to talk a little bit more about gases especially, but liquids and solids in class. As always, if you have any questions, let me know. Otherwise, I will see you in our next video, which I'm not sure what that'll be about, but I will see you then. Bye.